Good morning, everyone. I'm Ashish, and I will be presenting our work on differential privacy at risk. When this work was published, I was postdoctorate at ENS, and Deb was a postdoctorate at Chalmers, Sweden. I'm presently a lecturer at National University of Singapore, and Deb is a researcher at INRIA Lille. This work was funded by two projects, Singtel Research Lab at NUS, as well as BioQOP project at ENS. Without further ado, let me start with the presentation. I'm sure that at Puppets, everyone is familiar with the differential privacy. Our work exploits a few caveats in the definition. So for the sake of completeness, let's start with it. Differential privacy is defined for a randomized algorithm. It is characterized by the parameter epsilon that bounds the indistinguishability between the outputs of the algorithm on two neighboring datasets. We call a randomized algorithm to be epsilon differentially private if it satisfies the inequality shown in the equation on the screen. Epsilon is also known as the privacy budget. We find two issues with the existing formulation. Firstly, the definition is a worst case guarantee. The inequality in the earlier definition holds not only for all possible neighboring data sets, but for all possible outputs. This is indeed a worst case guarantee that requires high amount of noise in the randomized algorithms for strong privacy guarantees. Application of the off-the-shelf privacy preserving mechanisms such as the Laplace mechanism without a careful analysis end up in suffering a higher loss in the utility. For traditional businesses, the utility of their products is of the essence. Business-oriented minds are always ready to take risks that can be quantified. Therefore, instead of providing the worst-case guarantee, we envision a privacy guarantee with a quantifiable risk as a good compromise. The second issue is the abstract nature of the definition. Businesses understand metrics that can be related to monetary values. A non-technical person would need to invest a significant amount of time to understand the caveats in the mechanisms to get a meaningful result. We observe that there is a need to bridge the gap between this abstract definition and the monetary value. We address these two issues in this paper. We propose privacy at risk, which is a probabilistic extension of differential privacy. It provides a way to fine-tune the privacy risk of a differentially private algorithm. We provide closed form solutions for the fine-tuning of the Laplace mechanism. To address the second issue, we propose a cost model that bridges the gap between the abstract privacy level and a monetary budget for a project in a company. We instantiate the cost model by putting it in the context of GDPR. Let's start with the definition. We define privacy at risk as a probabilistic extension of the differential privacy definition. The proposed extension is inspired by the value of risk concept from the risk analysis literature. Value at risk quantifies the loss in the investments for a given portfolio and a confidence bound. In the same spirit, risk in the proposed definition, which is quantified by the parameter gamma, is an upper bound on the probability that a randomized algorithm fails to satisfy differential privacy. To keep the definition as general as possible, we explicitly denote a privacy preserving mechanism by the parameter f, which is query, and theta, which is the space of parameters, as well as the space of query specific parameters. Researchers have so far proposed multiple extensions of the vanilla definition. We list the most relevant extensions here. Approximate differential privacy, also known as epsilon delta differential privacy, is by its nature a non-probabilistic extension of differential privacy. The definition itself does not impose a direct connection between epsilon and delta. Delta parameter is simply a slack in the inequality definition. Random differential privacy and probabilistic differential privacy, they are indeed closely related to our definition, which we will see soon. Concentrated and Renyi differential privacy are stronger but yet more abstract definition extensions of differential privacy. Instead of bounding a privacy loss, they bound the moments of privacy loss random variable, and which sets these works apart from our work. We also assess the traditional properties such as post-processing and convexity, as well as composition for the proposed definition. Meiser et al., they have proved that any probabilistic extension of differential privacy cannot satisfy post-processing property. So does the privacy at risk does not satisfy post-processing property. Privacy at risk, although it does satisfy convexity property. In theorem 3, we have extended the proof for advanced compositions in differential privacy to adapt to privacy at risk. You can already see the resemblance in the result. So far, we have talked about the definition and related properties. Now let's look at how one can compute privacy at risk for a particular mechanism. To compute the risk gamma in the definition of privacy at risk, we have to account for multiple sources of randomness. Firstly, it can be explicit randomness induced by the privacy preserving mechanism. A privacy preserving mechanism with one set of parameters can indeed satisfy this privacy guarantee with another sets of parameters. For example, one differentially private algorithm can always is naturally two differentially private, but it can also be zero point 0.5 differentially private with certain risk. Secondly, to compute the risk, we can consider implicit randomness induced by the data generation distribution. The vanilla definition demands the bound to be true for all possible pairs of neighboring data sets, but not all possible neighboring pairs are equally likely to appear in the practice. We can exploit this caveat to provide a quantifiable bound on the risk. Such computations require us to work under a specific noise distribution as well as data generation distribution. Therefore, we instantiate this idea on a widely used Laplace mechanism. The Laplace mechanism is characterized by two parameters. Just like most of the mechanisms, it requires sensitivity, which depends on the query, and the privacy budget. Let's go case by case. Let's consider the first case of explicit randomness. In this case, we assume that all neighboring data sets are equally likely to occur, and we assume that the sensitivity of the query is also known. Therefore, for a specified value of say epsilon 0, the Laplace mechanism is already epsilon 0 differentially private. What we are interested in is it epsilon differentially private for any value of epsilon that is less than epsilon 0. We compute a closed form formula in theorem 4, which is shown as equation 2 on the screen, that connects epsilon 0 with epsilon and gamma. In this plot, we show the relationship between epsilon and gamma for the Laplace mechanism with different parameters. If you can focus on the blue curve, you can see that one differentially private mechanism is almost 84% of the times zero point 0.8 differentially private. By sliding along these curves, one can fine-tune the Laplace mechanism. Why would one do this when it is already known that the mechanism is one differentially private? A privacy budget of zero point 0.8 is indeed a stronger privacy guarantee than 1.0. It can be profitable for companies to provide a stronger guarantee with a quantifiable risk than providing a weaker guarantee. Additionally, the privacy budget of 1.0 induces a smaller quantity of noise than the privacy budget of zero point 0.8, and hence it offers the higher utility. Thus, we can obtain a better utility with a stronger privacy guarantee, of course, under an acceptable risk. In the interest of time, we will provide just a quick summary of the rest of the cases. In the second case, we study the randomness inherent in the training data set. Therefore, all pairs of neighboring data sets are not equally probable. It allows us to relax sensitivity computation. Sensitivity is, in the end, a worst case value. It is an upper bound on the change on the output of the query for neighboring data sets. We define sampled sensitivity, which is an estimate of the sensitivity computed by accounting for the noise induced by the data generation distribution. We provide an upper bound on the sampled sensitivity, which can be tuned according to the specified risk. In the third case, we consider the coupled effect. It computes the risk for a specified privacy budget as well as the sampled sensitivity value. So far, we have discussed how we can fine-tune the privacy-preserving mechanisms using privacy at risk. It has indeed been an abstract discussion. So let's move to the second contribution of the work, which indeed reduces this abstractness. All business entities that deal with the data from EU citizens, they are abided by GDPR. Article 82 in GDPR states that every user has a right to seek compensation from the company in case of a privacy breach. In such a case, a company needs to reserve a budget for an unfortunate event of privacy breach. We will show you how privacy at risk helps in such a case. Let E be the compensation budget per stakeholder in the case of privacy breach. E epsilon be the compensation budget per stakeholder if the company provides epsilon differential privacy solutions. A cost model is a function that establishes the connection between E and epsilon. The cost model has to satisfy following properties. Firstly, E epsilon should be less than or equal to E for all values of epsilons. If a company uses non-trivial ways to minimize privacy breaches, it should not pay the same compensation it would have paid had it not taken any privacy measures. Secondly, E epsilon tends to zero as epsilon tends to zero. When epsilon is zero, all outputs are equally likely. Therefore, it does not make sense to that such a useless mechanism would have revealed something which is useful. Therefore, thirdly, E epsilon tends to E as epsilon tends to infinity. When epsilon grows, the privacy guarantee of the mechanism weakens with it. Therefore, in the worst case, E epsilon should be same as E. Lastly, the cost model should be monotonically increasing function of epsilon in between. Multiple functions satisfy these four characteristics, but we chose one particular function that is a convex function. Most of our results naturally extend to the other choices as well. We can further extend the cost model of differential privacy to privacy at risk. We can show that epsilon zero differentially private mechanism can be epsilon gamma privacy at risk for a certain choices of gamma and epsilon. Such a mechanism satisfies epsilon differential privacy with gamma probability, and with 1 minus gamma probability, it is still epsilon not differentially private. This extension will justify the choice of convex function. The convex combination of convex function is in the end a convex function. Thus, the cost model for privacy at risk is a convex function. The convexity ensures the existence of a unique value of epsilon that minimizes the overall budget. Let's have a realistic illustration to help you understand the advantage of this formulation. Let us consider an organization of 100 employees which is working on obesity survey among the employees. Actuarial research show that a person can expect up to $5,500 of increment in their health insurance premium if the obesity related status is revealed. Let that be our estimate for E. The organization uses, let's say, zero point 0.5 differentially private Laplace mechanism. We can use the cost model and we can estimate the budget to be $74,000 approximately. The, the organization decides to use privacy at risk to fine tune the Laplace mechanism. It computes the optimal level of privacy using the convexity, and it turns out that it is zero, say 0.29, 0.64 privacy at risk. If we use these values in the cost model for privacy at risk, we will get the compensation budget of approximately $38,000. Thus, the use of privacy at risk allows the company to save approximately $36,000 without compromising on the utility of their analysis. We can also use privacy at risk to balance the trade-off between the utility and privacy. We had conducted experiments on the 2000 US Census dataset. We trained a differentially private ridge regression model to predict the income of a person based on the features such as marital status, education status, etc. We use RMSE as a metric of utility. The y-axis in red shows the utility for various values of epsilon, whereas the y-axis in blue shows the plot of privacy at risk confidence levels. Such a plot helps the data steward to choose a privacy parameter that satisfies utility requirement. For instance, if the desired RMSE cannot be more than zero point 0.2, the permissible parameterization for privacy mechanism should be zero point 0.8. You can look at the red curve. Looking at the privacy at risk curves, the data steward can fine-tune and report the same mechanism to be zero point 0.4 differentially private 60% of the times. Please refer to the full paper for further illustrations of how different cases can be used by data steward. In this work, we proposed a probabilistic extension of differential privacy. It provides a means to fine-tune the privacy preserving mechanisms if quantifiable risks are acceptable. If we provide realistic illustrations of how a data steward can use such privacy at risk to balance the privacy utility trade-off. We also proposed a cost model that helps to connect abstract privacy levels to a monetary budget. Such a cost model helps business organizations to use privacy solutions with ease. We also illustrate how the choice of a convex function assists in the use of privacy at risk to fine-tune the privacy parameter to minimize the compensation budget. To conclude, we believe our work helps non-tech businesses non-tech business entities to choose an appropriate privacy solution without an extensive overhead of privacy expert. Thank you.